Welcome to the deep dive. We take stacks of sources and, well, really try to boil them down into the key insights you need. Today, we're tackling some really fundamental questions about, well, everything. Basic physics, you stand on a beach and there's just this incredible complexity, isn't there? The waves crashing, the sand, the sky, even like your own thoughts swirling around. It's a lot.
Yes, it really is an astonishing amount of stuff happening all at once.
And it makes you wonder, right? Can all of this huge variety of things we see and experience actually come down to just a few basic building blocks? A small number of elemental things and forces just combining in endless ways?
That's the core question, yeah.
Yeah.
That's the grand quest of physics.
So our mission today is to unpack how physics tries to understand the world. We're drawing directly from some foundational ideas, specifically from the Feynman lectures on physics. We want to trace that journey physics took to simplify things and, see where we are now. Okay, let's unpack this.
What's fascinating here, I think, is just the sheer ambition of it all. Physics isn't just about describing stuff. It wants the underlying rules. Feynman uses a great analogy. Imagine the universe is like a giant chess game played by gods, maybe.
Okay.
And we're just watching. We can't ask the players what the rules are. We just have to figure them out by observing the moves.
Yeah, I like that. So fundamental physics is figuring out the rules of cosmic chess.
Exactly. And knowing the rules gives you that fundamental understanding, even if you can't predict, say, every single move in a super complex game. That's just too complicated. But you get the basics.
So we're like cosmic detectives trying to piece together the universe's instruction manual. And the way we've done that historically is the scientific method, right? Observation, reason, experiment.
That's the toolkit. Careful observation, logical thinking, and then testing your ideas with experiments.
Yeah.
Crucial.
Right. And how do we actually test these rules once we think we figured one out? You mentioned deduction.
Yeah, there's sort of three main ways Feynman talks about. First, sometimes you find, or you can set up, really simple situations. Think of just like a couple of chess pieces in a corner away from the main action.
Okay, isolated.
Right. In those simple cases, you can often predict exactly what should happen based on your proposed fundamental rules. Then you check, does it actually happen?
Got it. Like a controlled experiment. What's the next level up?
The second way is checking less specific rules. Rules that you derive from the more fundamental ones. Like in chess, the basic rule for a bishop is it moves diagonally. From that, you can deduce a simpler rule. It always stays on the same color square. You can check that rule without knowing every diagonal move it made. But, and this is where it gets really interesting in physics, sometimes you find that bishop suddenly on the wrong color square.
Whoa.
And that's not necessarily meaning the old rule was wrong, but maybe incomplete. It means there's a new rule or something more fundamental going on. Maybe the bishop got captured and replaced, or maybe the rules are different than you thought.
So those moments, the wrong square moments, are where the breakthroughs happen.
Absolutely. That's often where the most interesting physics lies, where the existing rules don't seem to work. That's how we find the next layer.
That's a powerful idea. Okay, so simple setups, derived rules. What's the third way?
The third is, well, it's approximation. It's rough, but powerful. Like, you might not track every pawn in a chess game, but you can often get the gist of a player's strategy. Are they attacking the king? Controlling the center?
Right, the big picture.
Exactly. In nature, we can often understand the general behavior of a complex system, like the pressure of a gas, without tracking every single atom. It's a crude understanding, but incredibly useful.
Okay. And physics has this history of trying to bring different phenomena together, right? Not just different rules, but whole areas like heat and mechanics or electricity and magnetism.
Oh, absolutely. The drive has always been towards unification, to see that seemingly different things are just facets of one deeper reality.
How surprising must it have been when they first connected heat and motion, or electricity and light?
Tremendously surprising, I imagine. Realizing heat is just atoms jiggling. That's huge. It connects thermodynamics to mechanics.
Right.
And then discovering that electricity, magnetism, and light are all just different dances of the electromagnetic field. That was revolutionary.
And that quest continues, right? Because we keep finding new things, new particles, new forces.
Exactly. Discoveries like X-rays, or later, mesons, they constantly force us to expand and refine those unified pictures. Physics is never finished. It often looks, kind of messy in the active areas, but that's the sign of progress. It's dynamic.
So let's talk about that picture before things got really messy with quantum mechanics, say around 1920. The classical view, what was the stage like?
The stage was pretty straightforward, yeah.
Yeah.
3 dimensions of space, good old Euclidean space, and time was just time, a separate thing ticking along.
And the actors on the stage?
primarily particles, atoms, basically. And these particles had properties like inertia. They keep moving unless a force acts on them.
And the forces.
Well, there were the really complicated short-range forces. The sticky forces holding atoms together to make liquids and solids, explaining things like why salt dissolves or how molecules interact. Very complex.
Okay.
And then there was gravity, much simpler. A long-range attraction between any two objects with mass falling off with the square of the distance.
But why do these forces exist? Was that part of the classical picture?
Not really why, in a deep sense.
Yeah.
The focus was more on describing how they work mathematically. The why is often a deeper question.
Okay. But this classical particle view was super successful, right? Explaining everyday stuff.
Oh, incredibly successful. Think about gas pressure, like atoms bouncing off walls, wind, atoms drifting together, heat, just the random jiggling motion of those same atoms. Even the sound was understood as waves of density passing through these particles.
And we knew about different kinds of atoms back then.
Yep. Based on chemistry, scientists had identified about 92 different types of atoms, the elements. They were seen as the fundamental building blocks.
Okay, so gravity works for planets and stars, but those short-range forces holding atoms together, gravity's way too weak for that, isn't it?
Way too weak. Utterly negligible at that scale. So that pointed to a different force, a much, much stronger one. Electricity.
Ah, right.
Think of it like gravity, but vastly more powerful. And with a key difference, gravity is always attractive. Electricity has two kinds of stuff charge, positive and negative.
And likes repel and likes attract.
Exactly.
Bro.
Which leads to a fascinating puzzle. If atoms are full of these powerful positive and negative charges, why don't they exert huge forces on each other from far away? Why does matter seem mostly neutral?
Right, the near-zero force thing. How does that work?
It's because the positives and negatives inside an atom are almost perfectly balanced. They cancel each other out when you look from a distance.
Okay.
But get them close enough, and they start to see inside each other. The charges can rearrange a bit, and then you get really strong interactions.
How strong are we talking?
Okay, get this. Feynman gives this amazing example. Take two tiny grains of sand, like a millimeter across. Put them 30 meters apart. If all the electrons in one grain repelled all the electrons in the other, and protons repelled protons, without the cancellation from the opposite charges, the repulsive force would be 3 million tons.
Wow. 3 million tons.
But
Between two specks of sand.
3 million tons. It just shows the unbelievable power locked up in electrical forces and how incredibly well balanced it normally is. Tiny imbalances are what cause static electricity and things we actually notice.
That really drives it home. Okay, so this classical view also started to give us a picture of the atom itself.
Yes. Eventually, the model became a tiny, heavy, positive nucleus at the center.
Protons and neutrons we know now.
Right, though neutrons came a bit later. And surrounding this nucleus were light, negative electrons, much lighter. And the key insight was that the chemical behavior, how atoms bond and react, depends almost entirely on the number of those outer electrons.
So carbon acts like carbon because it has 6 electrons.
Precisely. Element number 6. All that complex chemistry boils down to electron count and arrangement. It's a beautiful simplification.
But then the idea of forces acting directly at a distance, even for electricity, started to run into trouble, which led to the idea of fields.
Exactly. Instead of charge A directly pulling on charge B across empty space, the idea became charge A creates a condition in the space around it, a distortion. We call that the electric field.
Okay.
Then charge B, if it's placed in that field, feels a force because of the field at its location. So 2 steps. Charges make fields, and fields exert forces on other charges.
And this helps explain delay. You mentioned delay earlier.
Yes. If you wiggle charge A, the field changes. But that change doesn't happen instantly at charge B's location. It propagates outwards like a wave.
Ah, like ripples on a pond.
Exactly like ripples. And if you wiggle charge A back and forth, you create waves in the electric field. Now consider the delay. If charge A moves, charge B responds a little later. This difference in motion, this relative motion, is where magnetism comes in.
So magnetism isn't really a separate force.
It's fundamentally linked to electricity through this field concept and the finite speed of light, the speed at which these field changes propagate. They're 2 sides of the same coin, the electromagnetic field.
Like your quark analogy, jiggling one quark makes waves that move the other one later.
Precisely. The field is the medium, like the water.
And here's where it gets really interesting. These waves in the electromagnetic field, that's light, and radio waves, and everything else.
That's the mind-blowing part, yes. All of it. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, they're all electromagnetic
It's
waves.
just different frequency.
They're different frequencies, different rates of jiggling the charge, essentially. Slow jiggles give you radio waves like 500 be 1,000 kilocycles per second for AM radio. Faster gives you FM, TV, then radar.
Okay.
Faster still, around 5 times 10 to the 14 cycles per second, your eyes start to detect it.
Yeah.
That's visible light. Red is slower, violet is faster within that tiny range.
And even faster.
Infrared is just below red, ultraviolet just above violet. Keep going higher frequency, you get X-rays. Higher still, gamma rays, which usually come from nuclear processes rather than electron rearrangements.
Wow. So there's this huge continuous spectrum.
Enormous. We can generate waves in labs up to maybe 10 to the 24 cycles per second. And cosmic rays hit frequencies like 10 to the 27 cycles per second. It's staggering.
So the light we see every day is just this tiny sliver. It feels so central to us, but to a physicist.
To a physicist, it's no more fundamental than radio waves.
Yeah.
Just a different frequency of the same underlying phenomenon. But yeah, obviously crucial for us. And remarkably, this unified picture was largely worked out before the next big revolution.
Quantum mechanics.
Right.
Around 1920 onwards. And this wasn't just refining the picture, it was changing the foundation.
Completely changing them.
Mm-hmm.
Even the stage had already been warped by Einstein. Space and time weren't separate anymore, but space-time. And gravity became the curvature of space-time. But quantum mechanics attacked the rules of the actors themselves.
Newton's laws just didn't work at the atomic scale.
Fundamentally wrong. Things at that scale behave, as Feynman puts it, nothing like anything you have direct experience with.
Which makes it so hard to grasp, doesn't it? Our intuition is built on baseballs and planets, not electrons. Requires a real leap.
A huge leap. And one of the pillars of this new physics is the uncertainty principle. Heisenberg. The idea that you fundamentally cannot know both the exact position and the exact momentum, which is mass times velocity, of a particle at the same time. There's a built-in fuzziness to reality.
And that fuzziness explains something weird, like why atoms don't collapse, the why atoms are so big thing.
Exactly. Think about it. You've got this tiny, tiny positive nucleus. Why don't the negative electrons just spiral right into it? Classical physics says they should.
Okay.
But the uncertainty principle says, if you can find an electron to a space as tiny as the nucleus, you'd know its position very precisely.
Which means its momentum would have to be incredibly uncertain, wildly fluctuating.
Right. It would have such a high and uncertain kinetic energy that it couldn't stay confined. It would immediately blast out. So electrons maintain a certain minimum elbow room, a minimum amount of motion and fuzziness, purely because of this quantum rule. Even at absolute zero temperature, there's this residual jiggling.
Wow. It's not that they want to stay out, it's that the rules of quantum mechanics force them to maintain that fuzziness.
Precisely. It's a fundamental constraint. And this leads to perhaps the most philosophically troubling aspect for some.
The randomness.
The fundamental unpredictability. Quantum mechanics says you cannot predict exactly what will happen in a given experiment at the individual level. You can't say when a specific radioactive atom will decay or exactly where a single electron will hit a screen after passing through a slit.
Only probabilities.
Only probabilities. This completely broke the old deterministic view, the idea that if you knew the starting conditions perfectly, you could predict the future perfectly.
That same conditions, same outcome idea.
Right. But Feynman points out, what does same conditions even mean? If you do an experiment in Stockholm and get one result, and do the same one in Quito and get another, you don't throw out science.
No, you figure out the conditions weren't really the same. Maybe Earth's rotation matters, or the magnetic field is different.
Exactly. The context matters. Quantum mechanics tells us that at the fundamental level, perfect predictability isn't part of the context. The ultimate test isn't philosophy. It's, does the theory match the experimental results? And quantum mechanics matches beautifully, even if it's weird.
So quantum mechanics doesn't just introduce uncertainty, it also unifies things even further, waves and particles.
Yes, that's another profound insight. Wave-particle duality. Everything, electrons, photons, atoms, exhibits both wave-like and particle-like behavior depending on how you measure it. There's no fundamental distinction anymore. It's all just quantum stuff.
Which behaves more like a wave at low frequencies and more like a particle at high frequencies?
Generally speaking, yes. The particle nature becomes more apparent when you're dealing with high energies and frequencies. This unification leads us to maybe the crown jewel of modern physics, QED.
Quantum electrodynamics. Okay, what's the core idea there?
It takes the electromagnetic field that we talked about and makes it fully quantum mechanical. and it introduces the particle associated with that field, the photon.
The particle of light.
Particle of light, yes. QED is the theory of how electrons and other charged particles interact with photons, and that is incredibly, incredibly successful.
So what does this all mean? You said it explains almost everything.
Basically, yes. QED, in principle, underlies almost all ordinary phenomena you encounter. Everything except gravity and the processes happening inside the atomic nucleus.
Like what, specifically?
Well, the way billiard balls bounce. Fundamentally, QED interactions between the atoms. Wires moving in magnetic fields. QED. The specific heat of gases. QED. Why neon signs glow. QED. The density of salt. How hydrogen and oxygen make water. It's all down to electrons and photons interacting according to QED rules.
That's staggering. It covers all of chemistry, and therefore biology.
In principle, yes. All of chemistry is about electron interactions mediated by photons. And since life, reduced to its basics, is complex chemistry, QED is the fundamental theory underneath it all. It's the bedrock.
And it even made predictions, like new particles.
It did. It predicted the existence of the positron, the antiparticle of the electron, same mass, opposite charge. Dirac predicted it from his equations, and it was found experimentally soon after. It established the whole idea of antimatter.
And all this complexity comes from just a couple of basic inputs.
Largely, yes. The fundamental inputs for QED are basically the mass of the electron and the strength of its electric charge. From those two numbers, in principle, all this other complexity unfolds.
Incredible simplification. Okay, so QED handles electromagnetism and electrons. But then we get to the really strong stuff, the nucleus. What holds that together?
Ah, yes. The forces inside the nucleus are truly enormous, much, much stronger than electrical forces, but acting over incredibly short distances.
How much stronger?
Think about the energy release. A chemical explosion, like TNT, involves rearranging electrons, that's QED. An atomic bomb involves rearranging protons and neutrons inside nuclei. The energy difference is millions-fold. That gives you a sense of the scale.
Okay, immense forces. So is there a field in a particle for that too, like the photon for QED?
That was the idea proposed by Yukawa. He suggested a nuclear force field and predicted that its quantum, its particle, should exist. He called it the meson.
And they found it.
Well, sort of. They first found a particle in cosmic rays, the muon, which had roughly the right mass.
But it was the wrong particle. Another wrong square moment.
Exactly. The muon didn't interact strongly with nuclei the way Yukawa's particle should. It was like a heavy electron, basically. A few years later, they found the pion, which did fit the bill.
So the pion is the nuclear force carrier, like the photon for electromagnetism.
It's a key player, yes. But the theory of nuclear forces, sometimes called quantum chromodynamics, or QCD now, though the details are complex, is much, much harder to calculate with than QED. Even decades after the basics were laid down, working out the precise consequences is still a massive challenge.
So theory is struggling a bit, but experiments, they just kept finding more particles. The particle zoo.
That's exactly what happened, especially with particle accelerators. Suddenly, there wasn't just the proton, neutron, electron, photon, pion. There were dozens, lambdas, sigmas, k-mesons, G particles. It became a zoo.
A mess, but an exciting mess, right?
Oh, absolutely. Very confusing, but hinting at deeper structures. People started looking for patterns, like Mendeleev did with the chemical element.
Trying to organize the zoo.
Right. And a big step was the idea of strangeness, proposed by Gell-Mann and Nishijima. It was a new property, a quantum number, that seemed to be conserved in the strong nuclear interactions that created these new particles, but not conserved in the slower, weaker interactions through which they decayed.
So strangeness helps sort them into families.
It did. It led to classifications. You had the baryons, heavy particles like protons, neutrons, and these new strange ones like lambda, sigma, sheet. We now know they're made of fundamental particles called quarks. 3 quarks make a baryon.
Okay.
Then you have mesons, medium-weight particles like the pions and the chemiosons, which carry strangeness. They're made of 1 quark and 1 antiquark. These also form families.
And then there were those really short-lived things, resonances.
Yes, particles that existed for such an incredibly short time. It was hard to know if they were real particles or just very brief energetic interactions between other particles. That's still debated for some.
What about particles that don't feel the strong nuclear force at all?
Those are the leptons. That family includes the electron, the muon.
The heavy electron we still don't quite know the purpose of.
That's the one. Why is there a muon, 200 times heavier, but otherwise just like an electron? Good question. We don't know. And then there are the neutrinos. We now know there are at least 3 types, one associated with the electron, one with the muon, and one with another lepton called the tau. Neutrinos barely interact with anything.
Okay, so baryons, mesons, leptons,
Yeah.
anything else?
Well, you have the force carriers, the photon for electromagnetism. The particles mediating the strong force are called gluons. The particles mediating the weak force are the W and Z bosons. And if gravity is quantized, there should be a graviton, though it hasn't been detected.
And some of these have zero mass, like the photon.
Right. Photon and gluon,
Right.
and possibly the graviton. Zero mass means they always travel at the speed of light. They can't ever be at rest.
So zooming out again, after all this complexity, we basically land on 4 fundamental interactions governing everything.
That seems to be the picture, yes. 4 fundamental forces or interactions.
In order of strength.
Okay. Number 1, strongest, the nuclear force, or strong interaction, holds nuclei together, acts between quarks via gluons. Strength is about 1. The exact mathematical law is known, QCD, but calculations are hard.
Okay, number 2.
Electrical interactions, electromagnetic force, acts between charged particles via photons. Strength relative to the strong force is about 1137, so roughly 10 to 2. The law, QED, is extremely well known and tested.
Third.
The weak force, or weak interaction, responsible for certain types of radioactive decay, like beta decay, where a neutron turns into a proton, electron, and neutrino, mediated by W and Z bosons. Strength is much weaker, about 10 to 5 relative to the strong force. Law is known, part of the electroweak theory.
And last and definitely least in strength.
Gravity acts between anything with energy or mass, presumably mediated by gravitons. Its strength is incredibly feeble, about 1040 compared to the strong force. The law is known, general relativity, but how it fits with quantum mechanics is the big unsolved problem.
That difference in strength is just astronomical. 10 to the power of 40 between gravity and the strong force.
It's mind-boggling. Why gravity is so much weaker than the other forces is one of the deepest mysteries in physics.
So this brings us back to what the source called the horrible condition of physics today. But listening to this, it doesn't sound horrible, it sounds unfinished. Excitingly unfinished.
I think that's a much better way to put it. It's not horrible, it's just incomplete. We've achieved incredible understanding, especially outside the nucleus. QED works, quantum mechanics works, space-time is our stage.
But huge questions remain. The origin of the universe. What happens at the tiniest distance scales where quantum mechanics and gravity might clash? A full handle on the strong force and why all these particles exist in the first place.
Exactly. That profusion of particles still feels like it should have a simpler explanation underneath. We're still, as Feynman said, groping toward an understanding.
But patterns are emerging, right? Relationships between particles, hints of deeper symmetries.
Absolutely. Things like quarks, the unification of weak and electromagnetic forces. Progress is definitely being made. It's a dynamic, messy, fascinating frontier.
Which maybe means the real beauty isn't just in the elegant rules we found, like QED, but also in the puzzle pieces we haven't quite fit together yet. So here's something to think about. What surprising new rule, what completely unexpected connection might be waiting just around the corner, ready to turn our current picture upside down again? What wrong square discovery is next?